Good morning and welcome to the University of Minnesota Design of Medical Device Conference 3 and 5 competition. I am Randy Schustel and I have the honor of facilitating today's event. Helping me throughout the event are Paul Rothweiler, Tricia Huntush, and Gary Williams, all from the Earl E. Bakken Medical Device Center at the University of Minnesota. Our thanks also to Professor Art Erdman for his vision in creating this conference nearly 20 years ago. As you can see on the slide, we are 19 years strong. Shortly, we will hear from 10 project teams with new and exciting medical device concepts. First of all, I will introduce our judges. Today we have these judges participating remotely, including Don Bardot, Abiomed, Mark Weed, Mayo Clinic, Ingrid Bowman, Becton Dickinson, Joe Elkhetib, Abbott, John Diedrich, Chip Solutions, Jayant Parthasarni, we call him JP at United Health Group, Stephanie Board from Boston Scientific, and Mike Hess, Medtronic. Thank you to our judges who have reviewed the videos and submitted questions in advance. We are all learning how to conduct these types of events virtually, and we'll combine some prepared material and some real-time content to give you, the audience, a great 3 and 5 experience. It is your opportunity to see 10 exciting medical device solutions and score along to see how your personal assessment lines up with that of our experienced judging panel. Our judges will score each team in 6 areas: clearly defined clinical need, quality of research and plan, innovation, quality of presentation, the ability to excite our audience, and responses to questions. Our format today will be to watch a pre-recorded video from each team, present a few questions from our judges, listen to real-time responses, and take a question or two from our audience via the chat line as time permits. The next slide shows our first 5 teams. The 3 and 5 competition winners will be announced by 9 a.m. tomorrow on the DMD website. And a special email will go out to our mailing list. Subscribe on the DMD website if you haven't already. Let's move ahead to the first team video. This is Eric Nickel from the Minneapolis VA Healthcare System.
Hi, my name is Eric Nickel, and I'm a research biomedical engineer at the Minneapolis VA Healthcare System. Today, I'm going to show you a novel prosthetic ankle-feet system that can improve access to footwear options for lower limb prosthesis users. If you look at panel 1 in the upper left, you can see that prosthetic feet are aligned for a specific shoe. If a foot is aligned for one shoe and you put on a different pair of shoes, the prosthesis will push your leg into unnatural, unhealthy positions. Currently, there are some feet on the market that allow the user to adjust the ankle position to accommodate different shoe heel rises, as shown in panel 2 on the right. The user pushes a button which releases the ankle, and then they move the foot to the desired position and release the button to lock the position again. Unfortunately, this cannot happen while standing, and often the users of such systems need to make the adjustment several times to get it close enough. If the alignment is off by even a little bit, it can cause secondary injuries to the knees, hips, lower back, and inside the prosthetic socket. The range of adjustment for these systems is limited to approximately 2-inch heel rise at most. At these heel rises and above, changes to the geometry of the shoe interior makes the foot fit poorly, resulting in difficulty donning and doffing the shoe and unsightly failure to fit the shoe if the foot is visible, such as in panel 3 at the lower left. Who wants to be a bridesmaid at their sister's wedding and be stuck wearing tennis shoes? Body image, including the ability to wear the clothing and footwear of choice, is one of the primary indicators of participation in meaningful life roles for persons with lower limb amputation. Ultimately, even current heel height adjustable prosthetic ankles and feet are a barrier to wearing the footwear of choice and can have a negative impact on participation. Our approach is a little different. Rather than making a foot that can fit many different shoes, we're leveraging the mass customization of 3D printing to make low-cost feet, each custom-made to fit a particular shoe the user owns, and a single ankle unit with a quick attach mechanism that allows feet to be rapidly and easily swapped out. This cartoon illustrates the intended clinical process by which the system would be provided. A person with lower limb amputation would bring their shoes to the prosthetist, who would take a few measurements. These measurements get entered into an application that morphs a digital model of a foot to specifically fit that shoe. This model is then 3D printed, and the foot is delivered to the prosthetist. The prosthetist then confirms the fit and alignment in the clinic, and the patient now has a new foot that fits their new shoes. With this system, we hope to make all footwear accessible to persons with lower limb amputations, while minimizing the burden of changing footwear on a day-to-day basis. We have structurally tested our 3D printed prosthetic feet with loads of nearly 1,000 pounds, as shown in the top left panel, and modeling indicates that there is still a large safety factor. We're continuing to refine the foot model to reduce weight and complexity, as well as test cyclic fatigue durability using the relevant ISO standard. The ankle unit shown in the lower left panel is made of a titanium core and aluminum housing, with internal rubber bumpers that can be swapped out in the clinic to suit the individual user. It provides anatomically appropriate range of motion and can fit in even very small feet, like a women's size 5. In the future, we'll be developing a more advanced digital foot model that preserves high-fidelity features, such as individual toes and bony prominences. A full-color, customizable cosmetic cover would also be an option in future versions. The cost to make a simple foot is currently around $60, but that's expected to come down at scale and as 3D printers get faster and materials become less expensive. Reimbursement for the total system could fit within existing CMS coding, but it's unclear whether existing coding would cover receiving feet beyond the first. But at an anticipated price point under $100, additional feet could reasonably be purchased out of pocket. It's also unclear at this point whether additional feet could be purchased as an aftermarket add-on, without requiring further visits to the prosthetist for each new pair of shoes, sort of like some cosmetic fairings are currently sold. This would place more control in the hands of the patient. At present, the intellectual property covering the system is owned by the Department of Veterans Affairs and the University of Minnesota. On behalf of myself and my co-authors, I'd like to thank you for your attention and wish you good health in these trying times.
Thank you to Eric Nickel from the Minneapolis VA Healthcare System and team. And we appreciate the presentation. A question from John Diedrich, Chip Solutions, on our panel of experts. Question to Eric: great job on the presentation. What is the market size for the product? Is FDA approval required? And what type of funding is required?
So the market size at the moment is unclear. In particular, one of the question marks that this system has is how well does it work for high activity prosthesis users? How many lower activity prosthesis users would be focused on having multiple footwear options available to them? There's still a lot of information that needs to be gathered about this type of system and its market to really be able to estimate those numbers. As far as FDA approval, there are some particular carve-outs for lower limb prosthetic components in the FDA regulations. Pretty much just general controls is pretty much about all that's required. So in that sense, it's pretty fast and easy to get lower limb prosthetic components approved for the market.
Very good. A second question from Stephanie Board, Boston Scientific. Have you pooled amputees to get voice of customer? If so, what was the overall feedback on the need? the willingness to pay, and to have multiple visits for fittings?
So those questions are actually ongoing. So that's part of the current funding mechanism that we have, is to study exactly that. This has been thus far primarily in a design and development stage, and we're now in the process of gathering information and feedback from lower limb prosthesis users within the VA system of care. As you can tell, the current events have made it difficult to do meetings and to actually show the system to veterans with lower limb amputation. But that is part of the plan and will be ongoing.
Another question from Don Bardot, Abiomed. Scalability is key for cost and convenience. Can the foot be optimally positioned without the patient being in person?
So that's exactly why. So the prosthetist takes some measurements of the shoe, and the alignment is built into the digital foot model. So in theory, the receiver for the ankle unit is in the same location relative to the ground for every pair of shoes. So basically, the alignment should transfer from foot to foot to foot, regardless of what shoe is being worn, unless they're wearing a different pair of shoes than that foot was originally designed for.
Very good. Paul, do we have any questions from our audience today?
No, not at this time.
Very
Oh,
good,
we just received one. I'm sorry.
All right.
What keeps the shoe from falling off?
The geometry of the foot itself. So traditionally, lower limb prostheses, prosthetic feet in particular, have to be slightly undersized to fit into the shoe because they're more rigid than a traditional, than the anatomy that it's replacing. And they have to be able to slip in and out. We can actually get a more intimate fit because you only have to put the foot in once and it can stay in the shoe. Because when you switch shoes, you actually take the entire foot shoe combination off and replace it with a new foot shoe combination. So it can fit more intimately. It's a little harder to get in, but once it's in, it's a more snug and intimate fit. Also, usually the geometry at the heel, there's sort of the back of the heel kind of curls up a little bit, and the shoe does the same. And so you're able to sort of get that little bit of physical connection through the heel as well.
An add-on to that question is, have you tried wearing a high heel to understand the fit?
I have not. I have not tried wearing different types of footwear. Some of the other researchers in our group have. I have not actually tried that yet.
Very good, Eric. We appreciate your presentation, your Q&A, and your responses. Best of luck to you and your team.
Thank you.
Next up, we will hear from Patrick Powell at Arbor Grace, care of jaundiced neonates.
Hello, and welcome to our presentation on the Blue Kangaroo smartphone-enabled phototherapy irradiance meter for the care of the jaundiced neonate in low-resource regions. Our team is seeking a seed or grant investment of $250,000 to move our development from proven device concept to market, where it will help change the life trajectory of neonates around the world. And Hello, and welcome to our presentation. And Dr. Isa Abdul Qadir. Dr. Abdul Qadir is from Ahmadu Bello University, serving low-resource families in northern Nigeria.
Randy here. We are having some difficulty hearing the sound on this video. We do not have audio at the current time. Gary, let's try one more time, and then if possible, move ahead to the next video and we'll return to this one.
Hello. Our cross-functional development team is located in 3 states, Michigan, Texas, and Minnesota, and 2 countries, the United States and Nigeria. The clinical lead on our project is Dr. Katie Satram from the University of Minnesota. The technical lead on our project is Mr. Patrick Powell of Arbor Grace, located in Detroit, Michigan. The other members of our team are Dr. Tina Slusher, Mr. Gary DeWitt, and Dr. Isa Abdul-Qadir. Dr. Abdul-Qadir is from Ahmadu Bello University, serving low-resource families in northern Nigeria.
Neonatal jaundice results from the accumulation of a substance called bilirubin in the blood. Bilirubin is what makes the skin yellow in jaundiced babies, as seen in the photo at the top left. High levels of bilirubin are dangerous because they can cause permanent brain injury, leading to cerebral palsy and deafness. Severe neonatal jaundice continues to be a significant problem, globally affecting almost 500,000 infants each year, resulting in a significant personal and societal burden. Neonatal jaundice is treated using phototherapy, as seen on the top right. Research has shown, however, that phototherapy often delivers subtherapeutic irradiance, which is the quantified intensity of light over a specific wavelength delivered. The ability to accurately measure irradiance of phototherapy units is essential for delivering effective treatment. Validation of phototherapy irradiance using an irradiance meter is often cost prohibitive, especially in low-resource areas of the world. This lack of irradiance tracking results in substandard equipment maintenance and thus reduced standard of care. This last graphic on your bottom right illustrates what's been described as the 1090 gap, that less than 10% of the world's healthcare resources go to diseases and health problems that affect over 90% of the world's population. These are often preventable deaths in low-resource settings, and we believe that neonatal jaundice is an example of this gap. Simple and affordable technological solutions for neonatal jaundice will have a lasting impact on children, their families, and society as a whole.
To understand if the irradiance meter could be made more affordable, our team benchmarked existing market solutions. In one example, we found similar consumer devices with near identical functionality costing 100 times less than medical device solutions. This gave us confidence that a more affordable device should be achievable with the right technology package. Our original concept on the left was an irradiance meter combined with a smartphone to achieve an affordable, accurate device with a high level of user ergonomics. After evaluating our first concept with various experts, we pivoted to a revised concept shown in the middle, whereby a wireless irradiance sensor connects by Bluetooth to a smartphone, offloading the data computations to the smartphone app. A working field-testable prototype was then built, combining an Android app with a wireless sensor. The prototype was tested both in the laboratory and in low-resource settings to check the viability of our new approach.
Now the results of our prototype testing. The graph at the top left demonstrates a strong correlation in irradiance measurements comparing our prototype device with a commercially available meter. These measurements were taken at 8 Nigerian hospitals across 20 different users. Next, we surveyed 30 Nigerian medical providers. At the top right, you can see that 100% of responders described a positive or very positive experience using the device, and 96% would be interested in purchasing one. Importantly, the estimated market price for our product is $299 US.
The device was quite a huge success and quite a bit of experience. It promises to provide a great deal of care providers who never had access to an irradiance meter an opportunity to have a friendly, easy to use and affordable device that will impact highly on the provision of phototherapy services in low income countries such as Nigeria.
To move our low-cost, high-impact irradiance meter to neonatal healthcare impact, we are seeking a $250,000 go-to-market investment. If you would like to partner, please contact us at the information provided on the final page. Our team would like to give a special acknowledgement to the Thrasher Research Fund, the University of Minnesota, Hennepin Healthcare, Ahmadu Bello University, Arbor Grace, Disher Engineering, Beltline Center, and Internet Mobility Cellular. Thank you for your help and support with our project.
Thank you, Patrick and team. From Arbor Grace, we have a few questions from our judges. First from Mark Weed at Mayo Clinic. Mark asks, can this technology be applied in more developed healthcare systems and even in the home, for example, to monitor the progress of home light therapy?
Yes, we believe it can. Our target is to improve care for low resource regions. That's where we started. Interestingly enough, in the last few weeks with COVID, there's been discussions about trying to move more phototherapy into the home just to reduce the burden on hospitals. And so there would be a potential business case to use this to allow nurses, maybe parents, but at least nurses or people using the device in the home for to ensure that the baby is getting the correct phototherapy dosage.
Thank you. A question from Don Bardot, Abiomed. Please help me understand the linkage between the need and the solution. Phototherapy often delivers subtherapeutic irradiance. So is the solution better measurement? And is there adequate access to phototherapy to close the remaining gap?
Yeah, so it's a portion of the answer to better phototherapy. So this is one of a handful of projects that we're developing to improve phototherapy with Blue Kangaroo. So his insight is spot on. This will improve phototherapy because it would allow care providers in low resource regions to identify, especially fake phototherapies where they use blue paint on lights in order to show the parents think they're getting phototherapy. Typically in low resource countries, it's cash, it's cash and carry for treatment. And so this would allow them to identify fake or worn out equipment. But even so, there is other aspects of jaundice in low resource countries that need to be addressed, which is access to lower cost equipment and higher durability equipment for the treatment of jaundice.
A really good question here from Joe Elkatib from Abbott. What is the reliability of your system and what happens in the event the therapy is interrupted due to Bluetooth connectivity issues?
Yeah, that's a great question. The answer to that is if there is Bluetooth interruption, then it would prevent the device from being used with the phone. I don't think that the risk is as high as, for example, if you're using a dedicated device and it gets dropped or broken, the larger devices. But at the same time, it is something that we have to take into account, with the design of our device. I believe in the final production version, we plan to use encryption, for the communication path between the device and the phone. And probably the final answer to that question is because it's low cost, it would be easier for a hospital to replace a device if it did become broken or malfunction due to misuse.
Very good. Paul, do we have a question from our audience?
Yes, we have a similar question from Ingrid Bowman at BC and Will Durfee from the University of Minnesota. They want to know if the more expensive device that you're replacing, does that provide more reliability? Or have you had an opportunity to push both systems to the limit, environmental, battery backup, power integration, etc.?
Yeah, it's a great question. And the answer to that is no. We did this as a proof of concept to prove that it could be done on a shoestring budget. But that would definitely be a part of the next steps, prior to market to do that type of durability testing for the final device. We actually don't anticipate, as an engineer, I think that we did a strong job with the initial development. But we definitely need to put it through its paces before we put it out in the field and use it in in actual human trials.
Thank you very much, Patrick, and the team from Arbor Grace. We wish you the best of luck with your device.
Great, thank you.
Next up, we have Etsy Campbell from the University of Texas on delivery and retention of intrauterine devices.
Retention of intrauterine devices in the immediate postpartum period. The immediate postpartum period presents an ideal time for an IUD insertion procedure. The woman is definitely not pregnant, conveniently co-located with her clinician, and most likely desires effective contraception to prevent an unplanned pregnancy, which typically occurs within the first year postpartum. When this happens, this short inter-pregnancy interval has been linked to an increased risk of fetal and maternal morbidity. For example, intrauterine growth restriction, spontaneous preterm deliveries, preeclampsia, just to mention a few, and mortality. The American College of Obstetricians and Gynecologists has suggested that immediate postpartum contraception affords an effective solution to reduce such morbidities and mortalities, and to achieve reproductive life goals. They additionally recommend the immediate postpartum IUD insertion procedure. Unfortunately, because up to 30% of IUDs inserted using this procedure are expelled, rendering the contraceptive ineffective, the procedure is underutilized. Our objective, therefore, was to design, fabricate, and evaluate a novel IUD insertion and retention device by tethering a commercially available T-shaped IUD to the uterine fundus of an immediate postpartum baboon. And this non-human primate was selected because of the anatomical similarity of its reproductive tract to that of humans. And this is the device that we developed. Our unique device consists of a helical needle attached to an IUD housing tube and activated by rotating its knob on the end. The introducer tube shields the helical needle from coming in contact with tissue other than the targeted uterine fundus. We attached an intracorporeal absorbable barbed suture to a T-shaped IUD and threaded the suture into the helical needle. The introducer tube is used to locate the attachment point on the uterine fundus. The helical needle inserter is advanced to the fundus through the introducer tube. The suture is deposited in tissue by rotating the knob. Upon device removal, IUD and suture tether are secured. When the uterus contracts during involution, the suture tether ensures the IUD remains in close proximity to the uterine fundus. For the pilot study, our unique device was used to deliver suture tether and attach IUD to the uterus of an adult postpartum female baboon using ultrasound guidance. At week 3 following the procedure, hysteroscopy imaging confirmed the absorbable suture still tethering the IUD to the uterine fundus. At week 6, ultrasound imaging showed the IUD central stem completely within the uterine canal, with its arms extended laterally at the uterine fundus. In summary, we tethered IUD to uterine fundus using our device. The suture was completely absorbed by the 6-week time point, which is typical of puerperium, after which the IUD was removed. The IUD neither migrated within nor perforated the uterus during the study. This is promising because the baboon's uterine cavity is smaller than that of an average-sized adult human. Our initial study appears feasible. A longer study with more robust control will provide more definitive results about long-term safety and efficacy of our device and method. Thank you so much for listening.
Thank you very much, Etsy. We appreciate you and your team and your innovative concepts. A question from Joe Alcatib from Abbott. He asks about the procedure. It would seem that the blunt edge would cause damage to the surrounding tissue. This is talking about the IUD housing. During advancement, have you thought about this potential risk, and have you identified a procedural solution?
So during the insertion procedure, we use a speculum for a smaller speculum to dilate the cervix before inserting our novel device. So that's, at least to the best of our knowledge, that prevents the device from coming in contact or bruising the surrounding tissue during the procedure.
And no issues on your testing with animals to date?
No, no issues. We did only a single pilot study to verify feasibility.
Okay. A question from Paul Rothweiler at the Bakken Medical Device Center. Is the helical anchor left after the IUD is removed, or is it removable?
On the helical anchor is not left. So basically the needle, the helical needle, is just a delivery device. We use it just to insert the barbed suture into tissue. And once you rotate it out, the only thing that's left behind in the uterus is the absorbable suture and the IUD that's attached to it.
Thank you. Question from Stephanie Board at Boston Scientific. Do we have an estimate of the product cost and reimbursement?
We do not have an estimate for the product cost. We have used very simple materials. They're all just simple tubing and 3D printed materials, and everything is mechanically attached together. So it wasn't super expensive to prototype either. As for reimbursement, that's a little trickier because reimbursement is, especially with healthcare in the United States, is dependent on insurance companies, and sometimes it's hard to determine what the insurance company would cover following delivery.
And then two follow-on questions. Do you have a feel for the size of the market opportunity? And do you have freedom to operate from an IP perspective?
So we do have a patent for this device. For the market size, it's hard to tell. What we do know is that about 45% of pregnancies in the United States are unintended pregnancies, and about between 3 and 49% of pregnancies are due to short inter-pregnancy intervals in the United States, and that's for about 3 million babies born in the United States every year. So that's kind of what we're working with.
A really great question from Don Bardot at Abumed. The solution seems very straightforward. Why hasn't it been done before, and what barriers exist?
So reimbursement for long-acting reversible contraceptions is one of the major issues, and then is the major issues with this device, and with reimbursement for long-acting reversible contraception is one of the major barriers to market, especially in the United States, again, because of insurance companies. And the other thing is that for a long time, IUDs were not favorably seen or viewed by both doctors and patients. But though that has changed in recent times because of the IUD's effectiveness, it's still challenging to inform the public of the benefits of this device, one, and just change their view of IUDs in general.
Very good. Yeah, often a challenge with new devices. Paul, do we have a question from our audience?
Yes, from Amy Stricker-Hume. Is your device compatible with standard IUD devices currently marketed, or would you be designing your own IUD?
Yes, it's compatible with standard IUDs currently marketed. So the IUD that we used here was a copper IUD, and that's a standard commercially available copper with the copper bands and the rings around the central stem IUD. And we've also tested it with the Mirena hormonal IUD as well.
Okay. From Ingrid Bowman from Becton Dickinson. In my opinion, the body needs to be free after delivering a baby to get back to normal. What's been the feedback from mothers for this device?
So I haven't conducted a formal study for feedback from patients. The issue we're trying to combat is the short inter-pregnancy intervals, and that a lot of mothers are very desirable of contraception right after having a baby, just to save the costs, because a lot of mothers desire contraceptives after pregnancy for the health reasons, and it's also really expensive. Taking care of a new child is also very challenging for new mothers, and for new mothers. And so while they desire contraception to prevent a pregnancy, sometimes it's difficult for them to use traditional hormonal pills just because it's dependent on patient, the effectiveness of a hormonal pill or hormonal contraception, oral contraception, is dependent on patient use. So while they desire a contraceptive, we try to make this a simple solution so that it's something they don't need to think about, and they know, patients know that they're covered contraception wise. And but no, I haven't done a formal study on feedback from mothers for this device.
Thank you very much, Etsy, and your team from the University of Texas. We wish you all the best with your device going forward.
Thank you.
Next up, we have Madeline Habib from the University of Central Florida, talking on patient-specific 3D printed laryngoscopes.
Hello, my name is Madeline Habib. My team and I are from the University of Central Florida in Orlando at the Prototype Research Development and 3D Printing Lab, also known as PD3D. Today, I will be speaking about our paper on the design and optimization of patient-specific pediatric laryngoscopes. A laryngoscope is a medical instrument used to examine the larynx. It consists of a blade used to push down the patient's tongue and lift up the epiglottis. However, the issue is that there isn't a wide range of sizes and shapes of laryngoscope blades for pediatric patients, especially in comparison to the adult range. But pediatric patients have diverse anatomical sizes and structures within their own age group. This can be the cause for neonates having the highest risk of intubation complications, and abnormal airway can cause physicians to improvise what blade sizes to use. Also, accessibility and sterilization of medical equipment have become a critical concern in healthcare. However, it has been proven during this crisis that 3D printing has become essential in the production of medical devices. Therefore, with advancements in 3D imaging, modeling, and printing technologies, we are introducing a solution through the design and fabrication of patient-specific, single-use pediatric laryngoscope blades at the point of care. This process will provide not only the addition of variable sizes of blades for pediatric patients, but specifically modeled based on each patient's anatomical structure. Build paths for modeling the laryngoscope fitted a curve where the curvature of the blade was used to compare the age, weight, and height of patients. Based on our findings, the greatest correlation was found between patient height and curvature, then weight and curvature. Therefore, we've concluded that height may be a better parameter when classifying and selecting laryngoscope blade sizes. It is interesting because in industry production standards, weight is the current parameter for selection. The Verathon Kaleidoscope Spectrum series has 3 different pediatric sizes within the low-pro family. From our results, the variability in airway length shows that Verathon's classifications for selection was based on weight and were inadequate. For example, patients in Group 2 had 19 millimeter and 16.5 millimeter airways, which would be better suited for low-pro S1 instead of S2, which extends past 29 millimeters. This shows that not only are laryngoscope blade sizes inadequately available, but perhaps the selection is at fault as well. Our methods for designing the blades was by obtaining anonymous CT scans of 15 pediatric patients. The procedure for each patient followed the same pattern, which included the software Houdini to read and reconstruct the patient from the DICOM files of the CT scans, and to then isolate the airway passage automatically. Using the extracted airway passage, build paths were created to construct a 3D model of the blade for fabrication. An outline of the path from the oral cavity to the epiglottis is produced, which is used to construct the patient-specified 3D printable blade. Using this set of algorithms and procedure allows the segmentation, reconstruction, and creation of the patient's airway and specified blade in a quick, automated way. Our technology is disrupting the standards on how we are currently selecting medical devices for patients, the design process by using patients' anatomy, and the fabrication method because we can now do it at the point of care. As shown on Verathon's size guideline chart when selecting laryngoscope blades for patients, selection is based off of weight. However, our method involves a possible change in how laryngoscope blades should be selected, and therefore there is a need to allow future work to expand our database to support the relevant correlations and to be able to print these blades for possible testing. There are different angles of how this method could be commercially viable. It shows a potential change in the medical equipment market as there is a huge business opportunity present in the way of positioning patient-specified medical device development, and not just with laryngoscope blades. We are evolving the way of the production of medical devices in real time, as having single-use, patient-specified equipment reduces risks of infection and help decrease cost of buying multiple medical supplies that may never be used. Also, many hospitals do not have 3D printers, so we can potentially bring popularity and business partnerships with hospitals and 3D printing companies as they can supply these printers. Also, the automated software program that segments, reconstructs, and creates the patient-specified equipment can be a potential business approach that competes with industry standards software like Mimix and Slicer, which are more hands-on and manual approach.
Thank you very much, Madeline.
Thank you. Hello.
We have a question from our judges, and this question comes from Mike Hess at Medtronic. 3D printing is powerful, but is it the best option for this type of a device? Or would it be better to have a portfolio of different shapes with more options than we have today? We're recognizing the time to print, the availability of printers, and some other low-cost manufacturing options. Is 3D printing the right approach?
Well, 3D printing has shown great importance in engineering medical devices, and it is growing continuously. There is a proven need for patient-specific devices, and we all want to have medical devices that are individualized for every patient. And the only way that that can be done, in our opinion, in a quick and clean manner is through 3D printing. And hopefully with the help of future partners, we will get this into the market to start applying to real patients as soon as possible.
Very good. And then a follow-up from Joe Elkatib from Abbott. What is your sterilization strategy? Can it be done at point of care?
Well, the part of disposability, the advantage of that is that sterilization isn't as high cost as it is to use a reusable blade. We haven't yet tested on patients yet, or really tested on or done any future work besides printing the blade on just after using the automated process. So future work will definitely involve figuring out a way to sterilize before going on to patient use and into the market.
And then a question from Stephanie Board at Boston Scientific. Thinking about the procedure, is it standard procedure today to have a CT scan as part of the procedure?
Well, we're thinking, for future partnerships, we would be thinking about involving hospitals to have 3D printers, and hopefully physicians will be able to be using these automated processes in order to have the patient-specified devices at the point of care using 3D printers. So yes, CT scans should be readily available, but definitely future work will answer that question.
Okay. And then from Don Bardot at Abiomed, for commercial viability, product quality of the device and quality of the image and segmentation seems crucial. What is your plan to have high quality devices and high quality segmentation?
Well, now that we have the automated process ready, we are currently looking for medical experts to help give us the feedback and funds to understand what we could further along with these patient-specific devices. Medical professionals, 3D printing companies are all important in order to make this successful. And our next step would be customizing these blades and potentially developing mannequins to test these blades. So we're at the developing phase next to the validation phase.
Very good. Paul, questions from our audience?
Yes, we have one from Tom Kramer of Kablooey Design. Sorry about that. What's the most common use environment for laryngoscopes? Is it an acute situation where decisions are made quickly? If so, would a user want to wait to get this made?
This is normally, well, intubation is usually done in an ER setting or also in a non-emergency setting. Our procedure right now will definitely not be used for emergency. At the entire process right now takes about 20 minutes to print the blade from the CT scan. So we are not there yet, but the goal is to go from CT scan to print in 5 minutes in the future, and therefore we are looking for maybe some potential partners to take this into the market, and we'll be here to help with the process.
Very good, Madeline. We wish you the best of luck and your team from the University of Central Florida. Thank you for participating today. Next up, we have Paige Moss from Children's National Hospital. Paige will be talking about pediatric catheter ablation and a torque tool that has been developed.
Hello, my name is Paige Mass, and I am an R&D engineer at Children's National Hospital in Washington, D.C. Today, I will be presenting a novel tool for improved control and maneuverability in pediatric cardiac catheter ablation procedures. Catheter ablation procedures are used for the treatment of cardiac rhythm disorders that are not well controlled by medication. Transvenous catheters are inserted into the heart and used to deliver therapy. The physician must maneuver the catheters through the heart from the outside of the body by pinching and twisting them. These catheters are small, ranging in size from 1 to 3 millimeter. Manipulating them requires significant finger dexterity and control, which can lead to overexertion and muscle fatigue. This is especially challenging in the pediatric population, where small stature and potential anatomical anomalies add further difficulty when manipulating the catheters. There are approximately 500,000 cardiac ablation procedures performed in the U.S. each year, with about 5,000 performed in the pediatric population. While many torque tools exist to improve the control and maneuverability of transvenous guide wires, these tools are too small to accommodate cardiac ablation catheters and pinch in a way that can cause damage to the internal structure of the catheter, potentially altering the therapy delivered. Our team has developed PeriTorque, a novel patent-pending tool to improve control and maneuverability of cardiac ablation catheters. The tool is made of a two-part base that securely snaps together in the manufacturing process and an enclosed sled. The base has a main channel for the catheter to rest in and rails for the sled to slide along. The sled has a groove that holds the catheter in place and distributes the force over a large enough area so as to not damage the internal structures. To use the tool, the sled is pulled back and rotated 90 degrees to the left, opening the tool. The catheter is then placed in the channel, and the sled is rotated 90 degrees to the right, closing the catheter in the tool. The sled is then pushed forward until it is securely holding the catheter. The main channel is sloped so that the catheter groove and the channel converge as the sled is pushed forward, allowing the tool to accommodate catheters ranging in size from 3 to 9 French. We conducted 4 main tests of performance on the tool, starting with grip strength. The tool was placed on a standard 7 French ablation catheter, with the sled advanced to a predetermined location based on feedback from end users of expected normal use. The tool and catheter were set up on an instron, and an axial force was applied to the tool until slip occurred. The tool began to slip at an average force of 31 Newton, which is approximately 10 times greater than the peak force needed to insert a catheter into a vessel. We then conducted slip torque testing with a similar setup. The tool was rotated until a drop in torque was observed. The average slip torque was observed to be 0.039 Newton meter, 5 times greater than the max torque exhibited when rotating a catheter in a vessel. Next, we investigated catheter performance at maximum grip strength. The sled was advanced to the point of failure while simultaneously recording catheter impedance and a simulated ablation waveform delivered through the catheter. The tool experienced failure at an average force of 554 newtons, nearly 2 times the force that can be generated by a human. There was no statistically significant change observed in catheter impedance or the simulated waveform. Finally, we performed simulated use testing to demonstrate the torque tool performed as well or better than manual finger manipulation. The catheter was inserted through a 2-foot piece of tubing to mimic femoral access. The catheter was then rotated to 90 degrees and 180 degrees, both by manual finger rotation and with the assistance of the torque tool. At both angles, the torque tool significantly outperformed manual finger rotation. In conclusion, we successfully developed a novel torque tool for improved control and maneuverability of cardiac ablation catheters, and demonstrated that the tool can grip with forces in excess of normal clinical conditions without damaging the internal electronics of the catheter. In initial simulated use testing, the tool was able to more accurately translate torque than manual finger rotation. In an upcoming preclinical study, we will investigate if the tool reduces muscle exertion during a simulated ablation procedure. Our team has contacted the FDA for initial feedback on the device and received a non-significant risk determination, which we will use to conduct a first-in-human feasibility study with IRB approval. We believe this tool will provide a significant contribution to improve cardiac ablation procedures for both physicians and patients.
Thank you, Paige. Thank you very much. I pronounced your name wrong, Paige Mass. I have a question for you from Mark Weed at Mayo Clinic. Mark asks, why is it more tiring to manipulate cardiac ablation catheters in pediatric patients?
In the pediatric patients, the vasculature is smaller. There's less room to move around. And also many of these patients that require ablation procedures also have congenital heart disease that may make the vasculature more complicated, tortuous vasculature, which makes it a little bit more difficult to move the catheters around. We think this tool would be beneficial in both the adult and pediatric population, but we're targeting the pediatric population first because of those reasons.
Thank you. A question from Don Bardot at Abiomed. How would you plan to go to market with this device?
Our plan would be to license the device to a catheter company, and they most likely would package it with their accessory kits and have that be the route for going to market.
And from Stephanie Board at Boston Scientific, did you test for damage with just impedance base, or did you also use contact force sensing catheters?
We did not use contact force sensing catheters, but that would be a good idea of something that we could test in the future.
Mm-hmm. And does the device also help to reduce catheter whip during the procedure?
I'm actually not sure about that, but that would be something that we could look into.
Okay. A question from Joe El-Khatib, Abbott. How does a catheter channel accommodate various catheter diameters while at the same time ensuring that the lumen is not pinched?
The catheter channel is sloped so that the sled and the channel converge as you push it forward, which can allow it to accommodate catheters ranging in size. But the way that it converges, the sled and the channel remain parallel to each other so it doesn't pinch.
Very good. Do you think the device would be helpful for other interventional procedures outside of electrophysiology?
Yeah, I think it could, depending on what they're using to insert into the vasculature or other spaces.
Very good. Paul, questions from our audience?
Yes, we have a question from Art Erdman at the University of Minnesota. What are the potential failure modes of your device?
We anticipate the failure modes to be tool breakage. As I showed in the one picture, the sled handle broke off in all of our testing of failure. The other failure would be catheter pinching or other damage to the catheter, which we are testing to ensure that that risk is minimal.
Any other questions, Paul?
No, sir. Thank you.
Okay. Thank you, Paige, and your team from Children's National Hospital. Best of luck to you and your device. Thank you. Next up is Sam Frischman and team from Stanford University to discuss selectively compliant annuloplasty rings.
Thank you for the opportunity to present at the 2020 DMD conference. We are a group from Stanford, and we will be presenting a selectively compliant annuloplasty ring to enable annular dynamics and mitral valve repair evaluated by in vitro stereovision. In a healthy heart, oxygenated blood flows into the left atrium through an orifice known as the mitral valve and into the left ventricle, where it will be pumped to the systemic circulation to provide oxygen to the rest of the body. When the integrity of the mitral valve is compromised, blood flows backwards into the atrium, leading to decreased pumping efficiency. This phenomenon is termed mitral regurgitation, or MR, and is the most prevalent cause of valvular heart disease. The mitral annulus is a ring of connective tissue that bounds the mitral valve orifice and anchors the mitral leaflets to the fibrous skeletal structure of the heart. The geometry and 3D dynamics of the annulus are thought to significantly contribute to valve integrity. Consequently, mechanical and geometric perturbations of the annulus, as are seen in MR, can lead to annular dilation, malcoaptation of the valve leaflets, and leakage. A major aim of surgical intervention is to restore annular geometry and ensure leaflet coaptation, and this is often accomplished through mitral valve repair with an implantation of an artificial annuloplasty ring. It is well known that the annulus is dynamic throughout the cardiac cycle, moving from a saddle-shaped conformation during systole to a flatter, more dilated shape during diastole. Current rings on the market, however, fail to consider these annular dynamics and could lead to undesirable tissue stretches and reduce mitral valve competence in the long term. Sam will now describe our approach to this clinical problem.
To address this need and enable mitral valve annular dynamics, we have created a selectively compliant annuloplasty ring. This ring consists of a nitinol core and 4 polymer segments that mimic the 4 primary morphologies found in a native mitral annulus. The manufacturing process begins with a thin piece of nitinol wire. We use a joule heating method to shapeset the nitinol in a 3D conformation that supports the formation of an annular saddle. Additionally, a PTFE filament is attached to limit the AP diameter. The 4 polymer segments are cast in a 2-part process, with the anterior and posterior sections cast first, followed by the left commissural and right commissural sections. We tested the ring in a porcine valve using the Stanford left heart simulator and compared the results to commercially available semi-rigid rings. The videos here show 3 example cases. At the top, no ring is embedded in the annulus, representing a dilated, unhealthy valve. Significant change in AP diameter is visible, as well as other undesirable characteristics. In the middle video, a commercially available semi-rigid ring is used. Even from visual inspection, it is clear that the commercial ring is greatly limiting angular motions. The ring simply moves up and down during the cardiac cycle. At the bottom, we see our custom ring. Unlike the previous cases, the custom ring is both stiff enough to correct the dilated valve and compliant enough to enable formation of an annular saddle, as well as other key properties of a healthy mitral valve. To quantify these properties and understand the motions in more detail, we use an in vitro tracking method. In order to minimize interference of measurement tools with biological structures when assessing annular dynamics, we opted for a computer vision approach to tracking fiducial markers. 4 types of rings were tested under analogous conditions in the left heart simulator. The first was a soft, low-stiffness silicone ring used to provide a baseline comparison. The second was a Physio 2 ring, chosen as a representative case for commercially available semi-rigid rings. Cases 3 and 4 were our custom ring, named DynaRing, with and without the PTFE filament. Testing without the filament is done to explore the effect of limiting the AP diameter. Literature in the field has outlined metrics to characterize healthy mechanical performance of mitral annuli, and we characterize DynaRing using these same metrics. Specifically, we look at the anterior-posterior, or AP, distance, intercommissural, or IC, distance, and mitral orifice area. In the figure at the top right, we compare the metrics for the 4 test cases, as well as a finite element model prediction of DynaRing's performance and literature control values of healthy annuli. The data shows that all 3 metrics for the control case were best matched by DynaRing with the PTFE filament. The poor performance of soft ring confirms the need for sufficient rigidity to stabilize the mitral valve annulus. On the other hand, the commercial semi-rigid ring prohibits natural annular compliance and results in rigid translation of the annulus. In contrast, DynaRing allows for in-plane variations and enables the formation of the characteristic dynamic saddle shape. Finer ring discretization with an increased number of segments may further improve results. Segment stiffness selection is an attractive feature of this product and enables the designer to match patient-specific requirements. In conclusion, DynaRing is a selectively compliant annuloplasty ring that has demonstrated similar dynamics as healthy annuli, outperforming semi-rigid rings in our studies. We look forward to your feedback to guide our continued design improvements.
Thank you, Sam. We appreciate your input and the work that your team has done. A question for you from Mike Hess at Medtronic. What are the clinical outcomes and measures of success that you would expect to improve?
Yeah, so in the pump system, what we were looking at were these specific metrics: change in AP diameter, orifice area, IC distance. But that's a great question because what we're really interested in is regurgitation. How much is this valve limiting the regurgitation? So clinically, once we get to those studies, we would look at through echocardiograms specifically how much improvement this ring is causing as compared to commercially available rings. And beyond that, we'd also look at forces that the ring is imposing specifically on the chordae, which is another kind of sign for long-term efficacy of the ring.
Very good, thank you. From Paul Rothweiler, Bakken Medical Device Center. Have you had a chance to cycle test the device, and how many cycles do you think this device will withstand?
Yeah, that's an excellent question. And because, of course, the heart goes through nearly 1 million cycles in 1 week. And so fatigue is a big risk. And we think part of the reason why many of the devices on the market are either essentially fully rigid or very flexible. And that was actually one of our reasons for choosing super elastic nitinol, because of its fatigue properties. So, we've cycled this annuloplasty ring, tens of thousands of times, but we haven't quite gotten to the necessary kind of fatigue testing.
Right. More testing to do. A similar question from Joe El-Khatib from Abbott. Have you considered the biocompatibility of your chosen polymer material? And have you considered the effect of aging, even shelf life, of your chosen material?
Yeah, that's a great question. So for the experiments, for this initial prototype, we used urethane specifically as our polymer for its kind of ease of casting and low cost. In the next iterations, we're hoping to use biocompatible silicones, and we have identified some that kind of fit the hardness and kind of Young's moduli values that we need. So that's a great point, and something that the next iterations of the prototypes will include.
And then from Stephanie Board at Boston Scientific, is the ring compliant enough to be utilized in a minimally invasive procedure?
Yeah, that's an excellent question as well. So right now, a large number of these surgical repairs are open heart, but the trend is towards these transcatheter procedures. And that's actually the biggest growing sector of the mitral valve repair market. And so, right now in the immediate future, we're hoping to have these annuloplasty rings that would work for the kind of open heart repair. But one of the nice things, again, about using nitinol in these polymers is that, the nitinol wire's minimum bend radius is sub-millimeter. So we're actually hoping to have a foldable version that can collapse into a catheter and kind of fit the transcatheter approach in the long term.
Very good. From Mark Weed at Mayo Clinic. Do you anticipate clinically relevant differences in performance of this device versus the current standard of care?
Yeah, so in the long term, absolutely. So what we hear from the cardiothoracic surgeons is that the current devices often they'll cause in the long term, 5 years out, issues with suturing and also remodeling and hypertrophy. And so they'll have to go in and do a second repair or kind of modify the existing annuloplasty ring. And so we hope that a selectively compliant version will minimize the stress on the surrounding tissue, minimize that hypertrophy, and result in something, a longer term solution.
And one final question, have you thought about use of this technology in the tricuspid space?
Yeah, absolutely. So of course there are, other valves in the heart, and We're starting with mitral valve because that's one of the kind of most common, it's the largest market. But of course, it can be the selectively compliant paradigm can be shifted to the other areas of the heart.
Very good. Paul, questions from our audience?
Yes, we have one from Kate Taylor of Boston Scientific. She says, very interesting concept. Following up with Paul Rothweiler's question, how do you ensure the durability of the nitinol polymer interface?
Yeah, that's a great question and relates to the fatigue. So between the polymers, we actually, so the cure times of the polymers we used are around 16 hours, and we actually pull the sections out of the mold after around 4 to 6 hours before and cast the other sections. So they cure, they bond together very well at the interface. And the nitinol wire is treated with a primer, and the surface can be kind of graded such that it bonds really well to the polymers. And of course, the final solution would be embedded inside of a sheath. So that would further kind of promote the sections kind of being held together.
Very good. Thank you, Sam, for your work. Important area to bring new devices to market and a growing market.
Thank you.
Thank you very much.
Thank you very much.
Next up, we'll have a team from the University of Missouri, Columbus to talk about respiratory arrest monitoring. Muin Enati.
Hi, did you know how the routine safety checks in psych wards might inversely affect the quality of care experience for both patients and clinicians? Here, we explore new technologies to reduce this burden. According to the American Psychiatric Nurses Association, there are multiple protocols in psychiatric wards to ensure that the patients are safe and their environment is free of harmful items. These routine checks are more crucial when the target patients also suffer from some cardiac or respiratory disease. Current protocols to monitor the high-risk patients at psychiatric hospitals require a staff member to enter each room every 15 minutes to put a light on each patient to visually ensure that they are still alive and breathing. This protocol was meant for fast intervention to save lives, but unfortunately, it is disruptive to the patients and also is a burden for care providers. When psychiatrists at the University of Missouri reached out to us, we suggested a non-wearable and non-invasive radar system. We teamed up with Nokia Bell Labs to use a commercial ultra-wideband radar from the yard. We hide the radar system above each bed and inside the ceiling and recorded information at the rate of 10 frames per second. Then, in a post-processing step, 3D imagery of the area of interest is constructed. By changing the configurations, we could move from a low-resolution coverage of the entire room to a high-resolution coverage of small regions of interest such as chest or abdomen area, where most of the respiratory movements of the body appear due to the movement of the chest rib cage or diaphragm. After zooming on the predefined areas, we computed the interframe energy deviation to calculate a signal, which looks very similar to the reference signal from the chest band. We recruited 14 volunteers and asked them to wear the chest band and lay on the bed to perform a simple respiratory maneuver. In order to simulate the episodes of respiratory arrest, the participants were asked to hold their breath for a few seconds. Our recorded radar waveforms not only show the inhale and exhale patterns, but more importantly, the hold breath episodes are clearly distinguishable and match the reference respiratory arrest timing. We also ask the participants to repeat the maneuver once on each side, including left and right shoulder, supine and prone postures. We then post-process the radar data to zoom in 3 areas to compare the abdomen and chest movements. The overall percentage error are as low as 4% for the supine posture, which is just 0.6 beats per minute error compared to the reference signal. To sum it up, this paper presents the application of ultra-wideband radar systems in monitoring psychiatric patients for adverse events of complete respiratory cessation. We proposed 3D reconstruction of specific regions of interest to detect episodes of hold breath, and also estimated the respiratory rate with an accuracy of up to 96%. We plan also to utilize this work in predicting sleep stages and assessing the sleep quality. Thank you all for your time and attention, and please share with us your questions, comments, and suggestions for future work. My name is Moin Enayati. I recently joined Mayo Clinic, and this work was the result of a short-term collaboration between our Center for Elder Care and Rehabilitation Technology at MU and Nokia Bell Labs during my PhD studies under supervision of Dr. Marge Skubik. Thanks again.
As Moeen pointed out, he is from the Mayo Clinic. And here for Q&A, we have Marjorie Skubik from the University of Missouri, Columbia. Thank you, Marjorie. Thank you. Question from Don Bardot at Abiomed. How would something like this work in practice?
So we have also installed the system in a psychiatric ward at the University of Missouri. Obviously, the paper that Moeen just discussed had to do with a lab experiment that we had done under controlled conditions where we had ground truth. In the psychiatric hospital, it's a lot more confined in terms of how you can actually use a system like this. They have to pay attention to very strict protocols about not introducing anything that could potentially provide a risk for their patients. And so what we did in the psychiatric hospital is to install a radar system into the ceiling over the bed of the patient. And we also installed a depth camera system in the ceiling, also over the bed, that we could use effectively for ground truth to be able to see exactly what's going on in the environment without monitoring them. So they can't have anything that is on the body or that has any kind of cables or anything else. And so having it mounted into the ceiling over the patient's bed seemed to be the best way of actually accommodating this. So our thought was that this would be a monitoring system that would then allow the clinicians to see, sort of get a live feed of what the current status is, and be able to test, first of all, whether they're in the bed or whether they're not in the bed. If they're in the bed, are they lying still? So you get a measure of restlessness. And then if they're in the bed and they're lying still, then you can actually get the breathing rate.
Yes, very good. Thank you for the additional description. And that aligns very well with a question from Stephanie Board at Boston Scientific. Do you see any issues with interference or noise due to other medical equipment in the room?
This is a pretty sterile environment. There typically isn't any other medical instrumentation in the room. Certainly nothing that would have any kinds of cables at all. So I don't anticipate any problems with that.
Question from Mike Hess at Medtronic. Do the normal volunteers correctly stimulate the target patient population? And how do differences in sleeping positions and medications affect the results?
So the experiment that Moeen described was done with healthy subjects in our lab, and so that does not really simulate the actual type of environment that you would have in the psychiatric hospital. But more recently, in the work that we've done where we actually have collected data on real patients in the psychiatric hospital, overnight data, we have about 20 nights worth of data now, continuously from, I think it's 10 p.m. to 6 a.m. And so we do see a variety of different kinds of environment, and that I think is the real challenge here, is to be able to accommodate the variety that you see in these patients, which are not necessarily sleeping on the bed in the way that you and I might sleep on the bed. And they may also put the covers over their head and they'll curl up. We have some examples of that. And so we've been testing with that population, and so far looks like it's working remarkably well. So at least it's very promising, and we're continuing to do data analysis on that.
Two related questions from Mark Weed at Mayo Clinic. How well would this technology adapt to different size patients? And does the patient chest have to be within a prescribed area?
Well, this is part of what we're testing now. So far, it doesn't look like it doesn't look like it will depend on the size of the patient or the position of the patient. That the real key is to be able to determine where that region of the body is that is the most sensitive for being able to pick up the respiratory information. And so that's part of what we're developing.
Mm-hmm. Thank you. Paul, questions from our audience?
Yes, similar question from Don Peterson and Ingrid Bowman from Becton Dickinson. Did the patients know the system was in the ceiling? Have you thought about the emotional consequence for the patients to have this device? And have you used psychiatric patients or non-psychiatric patients in this test?
So for the paper, the results in the paper, that was done in the lab, as I mentioned. But for the patients that we did in the hospital, that was indeed the psychiatric hospital. These were psychiatric patients. They were consented. Of course, they had to agree to participate in the study, and so they were well aware of the system, and they agreed to it. Our protocol was set up so that if the patient agreed, then we would turn on the system and monitor at night. If they did not agree, then we would not have the system turned on. So I have not received any report back from the staff at the psychiatric hospital that this was a problem for the patients. It might indeed turn out to be an issue for some of them, but so far we have not seen that. It's designed to be a pretty unobtrusive system. It's not actually visible, but of course for the study we did want to make sure people were aware that this was being monitored. The alternative with having a staff person come into the room, turn a light on every 15 minutes is actually quite disruptive to these patients. And so it may well be that this type of passive monitoring system would be less disruptive and may be viewed more positively than having that kind of manual interruption.
We have another question from Joe Al-Khatib, sorry, Joe, from Abbott. Was risk considered or assessed from constant radar exposure?
Yes, we did consider that. This particular radar system is very low power. The power level is comparable to cell phones, and it has FCC approval of the device. So we don't think that that will be a concern.
Very good. Thank you, Marjorie, for your feedback and response to questions. We appreciate you being here today, and best of luck to you and your team.
Okay, thank you very much.
Next up, we have Arash Manan from the University of Minnesota talking about measuring ankle proprioception.
Hello, I'm Arash Manan, PhD candidate at the University of Minnesota, and I'd like to present my work on a new system to objectively measure ankle proprioception. Before getting started with the problem, I'd like to start with defining proprioception. Proprioception is defined as the ability to sense the position and movement of the limbs and body. Proprioception is necessary for control of voluntary movement and muscle tone. It is also crucial for balance control and upright stance. Numerous adult neurological disorders such as Parkinson's disease, stroke, and dystonia, as well as pediatric conditions like developmental coordination disorder or cerebral palsy, are associated with deficits in proprioception, which profoundly degrade motor performance and motor development. In addition, one of the main side effects of pediatric chemotherapy is neuropathy, and as a result, proprioceptive dysfunction. Unfortunately, there is no sophisticated system to objectively measure proprioceptive acuity at the ankle joint, an essential joint for balance control. As such, the extent of ankle somatosensory impairments in neurological conditions is largely unknown, and the impact of ankle somatosensory dysfunction on sensory motor control is poorly understood. Current clinical evaluations are mostly qualitative with minimal precision. In addition, complete evaluation procedures are time-consuming, and only trained evaluators can conduct them. This always results in lack of proper assessment for treatment and makes monitoring the long-term therapies challenging. Our team has been working on a lightweight portable system that helps clinicians to precisely quantify somatosensory dysfunction in ankle joints by reducing the time and need for the skilled evaluator. The system incorporates psychophysical algorithms to precisely measure the somatosensory threshold of the individual. The evaluator only needs to follow the instruction from the developed application and move the participant's ankle into different positions known as a stimuli value. The precision of the system is 0.1 degree. After 20 trials, which will take up to 5 minutes, the application will calculate the threshold and will report it to the evaluator. This way, the need for the skilled evaluator is eliminated. The system is suitable for monitoring longitudinal therapeutic success by eliminating inter-rater variability. The next step of our work is to collect normative data for healthy population with different age ranges as a gold standard for the threshold. We are working on further development of the system and incorporating tablet-based games to facilitate proprioceptive training and rehabilitation. We are also developing systems for other joints and limbs. Currently, our team is collaborating with medical community to measure ankle proprioception dysfunction for children with cerebral palsy and cancer survivors. Finally, our system has potential for funding from clinical field to help them improve the service to the patients. Thank you for your attention.
Thank you, Arash. We appreciate your video and your ability to be here in person for Q&A.
Thank
The
you.
first question that I have from a panel of judges is from Mike Hess at Medtronic. Mike asks, is the measure of proprioceptive acuity consistent with current clinical methods, or will validation be required?
It is consistent, but that's a nice question. It is consistent, but the issue right now is that the assessment is the challenge. So usually when because they cannot challenge, basically precisely calculate it, what they do, they just move the ankle. Basically, the clinician just moves the ankle, and based on the sense that he gets, he will kind of like tell that, okay, is it better or worse? So they are manually moving the limbs. We have done the validation, and we have the data. Data is actually, I put the data in the paper, so the data is on the paper right now.
A question from Stephanie Board at Boston Scientific. How is the data collected with the algorithm transmitted to, is the algorithm transmitted to a computer or smartphone to receive the results of the evaluation?
Right now we have a tablet-based system. So there is a wire coming out of there's an encoder embedded into the device. So when we rotate the device, we can basically measure the movement, and that data will go to the software that we have developed, and basically we measure the data through that. And basically we just use the input, and based on the input, the software and the algorithm will find the next seamless value, and then the examiner needs to follow the instruction based on that.
As you work to change a highly qualitative test to a more quantitative test, how does the data collected via the device compare to a skilled evaluator?
So basically, there is not a good, I would say, way of doing that. So I think what had happened before in other type of measurement that we had, basically we need to measure a huge amount of participants. For example, for another study, we had 150 healthy adults. We tested a huge range of people, and then we found the normative data for those. So I would say there is not a good way to compare these two together, but if we have the whole idea here is that if we have a normative data of healthy adults, then we can compare everyone else to those. So basically we are introducing a new method instead of basically having the evaluator to test based on the evaluator's experience. We are basically removing that, and we're having objective system that uses basically the mathematics and algorithm that we have.
A question from Mark Weed at Mayo Clinic. How does your system work to measure dysfunction?
Basically, so what happens is that we move the ankle to different positions. One of the tasks is that. So we move the ankle to first position, coming back, we move it to the second position, coming back, and then there is a difference between these two stimulus. And the question is that which one went further? And we start, let's say, from 4 degrees difference, and then it goes lower, 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 and then there's a threshold. There's a place that you cannot differentiate between those two movements. So that is your threshold. And if you have people who have dysfunction in proprioception, they have higher values, higher thresholds. So by comparing their threshold to the normative data, we can tell that there's a dysfunction in the proprioception.
A question from Don Bardot at Abiomed. How much of a burden is the existing measurement to the healthcare provider? And how would you quantify the impact of reducing that burden?
So basically, if we follow the normal test that should have happened in the clinics, that takes 45 minutes. And because the physician or the expert person needs to follow that instruction, and it's time consuming, the patient only goes to for the visit for 1 hour. So there's not such a time for 45 minutes to test the patient. Usually they just don't do it. So that doesn't exist. And for example, for chemotherapy, for the dosage of the chemotherapy, what happens is that the physician, based on the experience they have, weight of the subject, they guess, and they go based on the experience on the dosage of the chemotherapy. And they don't really run any tests on the patients other than they just move the ankle. That's the only thing they do. There's not, because it's long, they don't do anything. But our system basically introduce a really fast objective method, which is less than 5 minutes, they can get the results. And even the nurse, before the patient going to see the physician, even the nurse can test them beforehand, and they can go with the data. So with that part, we are kind of like reducing the time drastically. And sometimes I know that in many clinics that they don't even test because it's time consuming.
Paul, any questions from our audience?
Yes, we have a question from Will Durfee from the University of Minnesota. He asks, how dependent are the results on the ability of the clinician to move the handle at the desired velocity?
It is dependent, definitely. It's a nice question. What we are doing, we are trying to control the velocity with basically with the software that we have. That we try to instruct the user to move on a constant velocity. The next step for us is to embed a motor. Then the motor will move the ankle. So then we will eliminate that part too. But right now the system is manual, but with a really simple motor, we are trying to make it more automatic. Then that issue will be solved.
Thank you, Arash. Best of luck to you and your team.
Thank you.
Thank you for attending. Next up is Hao Su from the City College of New York to talk to us about untethered electro-pneumatic exosuit for gait assistance.
We are a team of students from the City University of New York working on affordable soft exosuits to assist a variety of lower limb impairments that affect more than 200 million people all over the world. Robotic exoskeletons have demonstrated to be a potential solution to provide assistance and rehabilitation together with or in place of conventional physical therapy. However, their wide potential impact is hindered by the stiffness and high cost of commercial exoskeletons. The state-of-the-art devices typically cost more than $50,000 and are primarily developed for people with full paralysis due to neurological impairments.
To address these issues, we have been developing soft and affordable apparel for untethered assistance. As an example, this picture shows an embodiment to aid ankle dorsiflexion. A key contribution of our design is a vacuum-driven origami actuator that connects two braces placed on the wearer's shank and foot. It is made of a 3D printed skeleton wrapped by a nylon fabric and then sealed. When vacuum is applied, it contracts and exerts forces on its two attachment points. The exoskeleton includes a compact motion sensor on the thigh for gait intention detection and a waist belt containing the pump and a control board with electrical and pneumatic components. Here is a video showing the effectiveness of our portable exoskeleton.
At the Center for Wearable Exoskeletons here at TR Memorial Hermann and the University of Texas in Houston, we do a lot of studies using the different lower limb exoskeletons and robots. Many of the robots that we have right now are not practical to be used at home. So we are trying to design a robot that can be put on and taken off easily because it will be lightweight. It will be easy to manipulate. It's something that I predict will be very useful at home for many of our patients. This is not a device that will be produced by roboticists and clinicians that we will suggest to the end users. It's the other way around. The center of this really are the end users.
When I put this on, it actually helped me. I felt that I had more stability, it helped my balance, and my gait kind of went very natural. I felt very comfortable in the sense of, wow, this is going to be my friend.
I love it. It took about, a minute. Because it's pretty easy. I'm walking a lot lighter. It's very low profile. I don't hear noise when I'm walking. Everyday use, this is perfect.
They have to tell us what they need. They have to tell us what they want so that when we finalize the soft exoskeleton, it is something that will be useful, meaningful, something that will help them in their recovery and their activities of daily living.
Preliminary results are very promising. The main advantages of the proposed project are that, 1, it's cost-effective. The manufacturing cost for single actuator is less than $5, making the exoskeleton more affordable in comparison to rigid models. 2, it is lightweight. The entire weight of the exoskeleton, including the battery, is less than 2 kg. And lastly, it exerts high forces that are 6 times higher than the conventional soft robots. Furthermore, even though the device is initially conceived for ankle impairment assistance, its fully modular architecture allows this solution to be applicable to knee and hip joints impairments as well. Regarding its appeal to stakeholders, this technology creates value not only for users, but also for insurance and healthcare sectors, thanks to its low-cost nature. Based on the existence of solid prerequisites for concrete commercialization, we are working on advancing the technology to the point where it can enhance independence and the quality of life for people with both neurological and musculoskeletal disorders. To conclude, I would like to share with you some feedback from our collaborator.
Our medical center is the clinical collaborator with Dr. Su's lab. Soft DMG sensor technology is a human-machine interface that monitors the user physiology and varies the power assistance by maximizing the use of the residual or remaining function. Our group plans to conduct the safety and efficacy studies to investigate the usefulness of this technology. This new robot offers a suite of important enabling technologies, from sensors and actuators to AI for a variety of patients with lower limb paralysis. The most promising aspects about this innovation is not only the technology itself, but the translational value, the potential for affordability, and the way that the device will encourage user independence.
Very well done. Terrific video. Hao-Su, thank you for your work with the City College of New York. Thank you very much. Question here from Joe Alkatib Abbott. How does this technology's weight compare to current devices, and does that include the energy source?
Yeah, so the overall device, our device is about like 4 pounds. And the existing exoskeleton typically around like from like 20 pounds to 60 pounds. But to be clear, and our device, what we are talking about is a unilateral and a single joint device. And the commercially available exoskeleton, they are typically multiple joints, support powers the knee and the hip. But even for a single joint, our device is about like more than 50% less mass for a single joint.
And what type of energy source do you have?
Yeah, so basically it's battery powered and it's pneumatics driven. And the key feature of this exosuit is first is untethered. So we don't rely on external pump. So the overall system is pretty generally lightweight attached to the person. And because the origami structure, it can generate about 4 times higher force than conventional software actuator. That's why it's very portable, but it can also generate a high force. And yeah, so essentially it can last, the current device can last about 1 hour. Generally, it's able to cover, to support activities of daily living, because most people don't walk more than 1 hour in general. Yeah.
Very good. Question from Mark Weed at Mayo Clinic. Does this device compete with those others that provide electrical stimulation, or is this for a different category of patients?
Yeah, so I think FES is some kind of like a competitive product. So this one is primarily like a powered orthosis. So that's kind of like provides like a physical assistance. Generally belongs to exoskeleton, powered exoskeleton, this category, and basically class 2 device. But for FES, typically have some like fatigue issues, and I think this will be some like alternative. Like it's like a brace, but it's powered, can provide some like assistance, physical assistance during human locomotion. So I think this will be an alternative, not really to replace FES, but it can be used with FES together. For example, if the FES induces fatigue, maybe we can use the robotic system to provide the assistance besides the FES. So they can be used together or with the exosuit itself. Yeah.
Very good. A question from Stephanie Board, Boston Scientific. Do you see this device gaining reimbursement, or will patients pay out of pocket?
Yeah, I think this is something we are trying to understand in collaboration with Dr. Ann Spungen in Bronx, VA. I think Cigna is the only insurance company that covers insurance for exoskeleton, basically an exoskeleton called a Rewalk exoskeleton based in Boston area. So Dr. Spungen, she conducted like a clinical safety and efficacy evaluation to help Rewalk to gain the FDA approval. So basically, we are working with her to understand the FDA landscape and also the reimbursement model. But generally, from my personal feeling, because our device can cover a kind of broader population, it's beyond conventional people with neurological disorder. This can also help people with musculoskeletal disorder like knee osteoarthritis, and also it's much cheaper and more affordable. So we think this has a better opportunity to be included in the reimbursement system. But currently we don't know this, and we are working with Dr. Spungen to understand this the overall landscape.
Yeah. Okay. And a question from Don Bardot at Abiomed. 3D printing was highlighted as a feature of the original origami actuator. What advantages does 3D printing have or offer for the exosuit?
Yeah, so I think basically the key feature of this device is it can generate a high force, but the overall system is very portable, lightweight. The key kind of like invention is this origami structure that can amplify the force. It's kind of like a gear, fashioned like a gear, the inside of 3D printed structure. The origami structure is kind of like a gear, can amplify the force. So basically about 4 times higher than conventional soft actuator can generate. So that's the key part. And also using the 3D printing this way is very easy for rapid prototyping, and also it's pretty affordable. It's just a couple dollars to print the 3D structure, and also to have the fabric enclosure, kind of like the internal skin of the structure. So I think it's very convenient for rapid prototyping. In terms of like a mass production, I think there may be some other better, even more affordable manufacturing methods. Yeah.
Paul, questions from our audience?
Yes, we have a question from Paul Izio from the University of Minnesota. Can the device be easily modified as the patient's status changes, plus or minus?
Yes, so I think basically we have different kind of sensors on the person. So our primary sensor is the inertial measurement unit. So basically we can measure the joint angle and angular velocity of the person. So that's because walking and also walking speed. So we can calculate the walking speed because walking speed is considered kind of the new vital sign for human monitoring. So basically we can use the walking speed as one indirect kind of like a surrogate to understand the human behavior to, for example, to provide more assistance or less assistance. So basically based on different impairment levels, so we can provide different levels of assistance from the software level. From the hardware level, we can basically make a different size of like an origami structure, and to generate from like a small force, medium force to large force, to accommodate people with different levels of impairments. So yeah, that's how it works in terms of mechanical adaptability and also like software adaptability to accommodate people with different levels of impairments. Also, we think this probably can cover people with different, basically in the continuum of rehabilitation. Even in the acute phase, people probably can also use this. Because we mentioned this for overground walking, but actually people can also use this maybe in the acute phase. For example, they can use this to provide dorsiflexion and plantar flexion when the people still are on the bed. So that's a really a very affordable device, covers a broad spectrum like rehabilitation for people with different levels of impairments and in different phase of their like a rehabilitation process.
Thank you, Hao. Appreciate your participation today. Best of luck to your team from the City College of New York.
Thank you for organizing this. Thank you.
Our final team is represented by Carl Nelson at the University of Nebraska-Lincoln. to talk about a portal venomanometer.
Hi, I'm Carl Nelson, and we'll be talking about a portable venomanometer system for episcleral venous pressure measurement. The problem that we're addressing is to detect traumatic brain injury, particularly in the mild to moderate range. The difficulty of this arises because the typical methods that are used, for example in sports medicine or in the military, involve a relatively subjective cognitive performance test against the baseline. So it would be really nice to have a quantitative biomarker that tells us whether TBI has been induced. Fortunately, we do have a quantitative biomarker. Elevated intracranial pressure, ICP, has been linked to the onset of traumatic brain injury. However, ICP is really hard to measure. It's very invasive. And so we're interested in an alternative, newly emerging biomarker called episcleral venous pressure, which allows us to take a surface measurement of a vein on the eye and detect how much pressure it takes to half blanch that vein. We use a special device called an episcleral venal manometer, which is typically used in glaucoma research. And based on the coupling between pressures in the veins system of the eye and the cerebrospinal fluid in the brain, we have this relationship that allows us to use EVP as a quantitative biomarker for TBI. The problem is that since EVP is typically used in glaucoma research in a clinical setting, the equipment that's used to measure EVP is not really suitable for field settings such as locker rooms or battlefields. So instead of a slit lamp or an operating microscope, we want to get some kind of low-cost device that is more field deployable. So here's what we developed. It is basically an accessory kit for the existing venal manometer, where we package it with a fine adjustment mechanism, which allows us to precisely position the venal manometer against the episcleral vein in the eye, and a smartphone, which allows us to do image capture, image processing, data logging, and data transfer. We accessorize that with some added lenses and lighting, which help us to create the good optical conditions for getting high quality images. And we add a potentiometer onto the venal manometer because the reading on the dial is a reading of pressure, and we want to read that electronically and merge that with the image. So we actually put a potentiometer on there, use a processor to feed that reading back to the smartphone, aggregate the data, and overlay the pressure reading on the image itself. So within the app that's customized on the smartphone, we can take still or video images, manage the files, and adjust focus and zoom, and see the pressure reading overlaid on the image. So it's really kind of user-friendly. We've tested this in rabbits, and we've been able to show that there is a favorable performance of our integrated system to using the basic venal manometer in more of a clinical standard use scenario. You can see that we get really good image quality with rabbit eyes, and we can detect the half blanch condition that allows us to measure EVP. Cost-wise, we keep it relatively affordable. The venal manometer itself is under $1,000. We add a smartphone to it for a few $100s, and our added components, which are mostly off-the-shelf parts, are less than $500 added cost. And keeping it this inexpensive is really great because we've got a really big market that we can address. Globally, the concussion diagnosis market is estimated to be about $1 billion, and this breaks down for us into two really large, obvious market segments. One is sports medicine, and another is defense. And so these are our two biggest targets. Fortunately, the original venal manometer design is not a limiting factor in our ability to produce a commercial product out of this, because the original venal manometer patent is no longer active, and our main developments that are being added to this are mainly in the software that's being run on the smartphone to kind of pull all the pieces of data together and facilitate decision making about the presence or absence of TBI. Hope you enjoyed this presentation, and I'll be happy to take questions in the Q&A session.
Thank you very much, Carl. We appreciate your engagement and availability for taking some Q&A. First from Mark Weed at Mayo Clinic. Would a physician be required to run the device and make the measurements, or does it have to be a specialist?
Well, usually in the current workflow, it's a specialist because the device, the venal manometer device, is relatively esoteric. But moving forward, we would anticipate that it could be just a technician with minimal training. The tricky part is getting the device positioned against the episcleral vein, and with a little bit of training, a technician could be brought up to speed in how to do that, and then the device does the rest. Our device takes out the inter-operator reliability type issues with using this type of measurement.
Very good. Also from Mark, how long after TBI does ICP become relevant? Is it immediate, or does it take some time for this swelling to occur?
That's a great question. I don't actually know the exact number, but I imagine that it's pretty fast. Yeah, I don't have a number for you, but I could tell you more about the prevalence of concussion and mild TBI, which is actually a pretty strong motivator for this project.
Right, right. Yes, concussion diagnosis is very important these days. Is the device suitable for a remote or telemetry application?
Yeah, I mean, it's basically integrated with a smartphone. So anywhere where you've got signal, you could send this data back to the clinic if you had a remote, like a teledoc type scenario. Yeah.
Question from Stephanie Board at Boston Scientific. You stated that the IP has expired. Will you file for the app or algorithm that you are creating?
Yeah, I believe that's already in process. We had some discussions with our university IP managers and talked about device IP versus software IP and things like that. And they seem to lean towards the software side. And so we've just been following their lead on that.
When you think about potential markets in sports and military, do you see a path to reimbursement?
Yeah, it's a little bit tricky. I don't know the exact codes that would be used, but when I'm looking at reimbursement for concussion diagnosis and the associated conditions, most of the codes that I see in a quick internet search refer to the kind of neurological performance testing that's common nowadays. But I know that there are, codes for using this EVP, this venal manometer device, for other purposes, such as in glaucoma research. We have had discussions with the FDA about, risk that we may be adding to this, and we actually have a human subject study that's planned and been approved by our IRB based on that discussion with the FDA about adding minimal risk. And so although I don't know the exact codes, I'm pretty confident that there are reimbursement pathways for doing this. Since
Paul Rothweiler from the Bakken Medical Device Center says the highest cost in your build is the venomanometer at $975. Do you have ideas on how to build a lower cost unit?
Sure do. Haven't done it yet, but yeah. I actually have. I think that one of the weak points of our system is actually the manometer itself and the modality of measurement there. So I think there are ways to improve that device. So we'll see.
Don Bardot asks, what is the significance of being able to portably measure TBI, and how will you clinically validate this biomarker?
Well, I think the significance, well, let me start in reverse order. The clinical validation is partly done. We've done animal studies to show the correlation between ICP elevation and EVP elevation. And there's actually an equation that's well established in glaucoma research called the Goldman equation that relates the two. So the validation of the principle of using EVP as a biomarker is pretty well established now, even though it's not yet a commonly used biomarker for TBI. Sorry, I lost the other half of that question.
Oh, I was asking, how will you clinically validate, and what is the significance to portably measure?
Right, portability is key to use in sports medicine or in the military, because you just don't have the clinical setup in either of those environments.
Yes. Paul, any questions from our audience?
Yes, we have from Tom. Could this entire device be set of goggles, or does it have to be a standing unit?
I think it has to be a separate unit. The trick is positioning. So you have an immobilized patient, and you have to position the device against the episcleral vein. So you're touching the surface of their eye. And I think if you put it on goggles, the person standing there trying to put their goggles against someone else's eye, it would be too difficult to stabilize that contact, and could add risk to the workflow.
Thank you very much, Carl. Thank you for being here, and best of luck to your team from the University of Nebraska-Lincoln.
Thanks.
As we wrap up, I would like to say thank you to our presenters, our judges, our university staff, and our audience for attending today. We've heard from 10 strong teams and must now make some tough decisions. The presentations were really well done. Strong narratives supported by some great photos, graphics, and testimonials. Hopefully you've all taken away some thoughts on how to best operate in this pandemic environment, where we're highly digital, virtual, and remote. Today's connectivity tools enable us to collaborate and communicate with ease and efficiency, even when not physically together. One benefit of the new format is that attendees worldwide can participate without the expense and time and commitment of travel. In addition, the event is fully recorded and can be viewed at times convenient to all participants. Thanks especially to Gary Williams, Paul Rothweiler, and Tricia Huntash for their help in setting this up and finding a way to bring the 3 and 5 presentation to life. Enjoy the day, afternoon, or evening, and watch for the 3 and 5 competition results by 9 a.m. tomorrow on the DMD website, and a special email will go out to our mailing list. Thank you for joining us, and we will see everyone next year for the DMD 3 and 5 competition at the 20-year event. Goodbye.